One of the nice features of using tangent measures is that they often have better or improved versions of the properties that the original measure had. So in this video, we'll focus on what the density properties of a measure say about its tangent measures. We earlier defined densities for Hausdorff measure, but the definitions extend immediately to general radon measures. So given a radon measure mu and a point x, we define the upper S density to be the lim supremum as r goes to 0 of the ratio of the measure of the ball, bxr, divided by its diameter to the power s. And recall, diameter of the ball is just 2r. The lower density is similarly defined using limit infimums. And finally, the density of a measure is just equal to the limit of these ratios when the limit exists. Of course, it may not always exist. So for upper and lower density to be positive and finite at a point means that the measure on small balls around x is behaving roughly, though not exactly, like a power of r to the s. However, if this holds almost everywhere, then we'll see that for its tangent measures, this will actually hold for all balls centered on the support. Let's make this property more precise. So we say that a measure is L4's S regular if the measure of any ball centered on its support and of radius at most the diameter of the support is comparable to the radius to the power s. So some familiar examples of L4's regular measures are Lebesgue measure, and in fact the measure of any ball is just a constant times the radius. Now L4's regular measures don't have to be flat or smooth or have any smooth structure at all. As we've seen already, self-similar sets support L4's regular measures. If the upper and lower densities of a measure are finite and bounded almost everywhere, this effectively means that our measure looks L4's regular on small scales. We can actually make this statement more precise in the following theorem. So suppose we have a non-negative number s and mu is some radon measure in Rn. Then for almost every point where the upper and lower densities are positive and finite, if we let T of A be the ratio of the lower and upper densities, then for any tangent measure nu of mu at the point A, there's a constant c, so that the tangent measure nu is L4's regular with the following constants. So it's at most this number c times r to the s, and it's at least the same constant but times T of A times r to the s for any point x in the support of nu and for any radius bigger than 0. So we'll just sketch some of the ideas behind the less precise result that all tangent measures are just L4's regular, since the main ideas between this proof and the actual proof of the full result are quite similar, but these will be easier to present. So let E be the set of points where the upper and lower densities are positive and finite. We can split this setup into sets A sub m, where m ranges over all positive integers, and A sub m is the set of points where, for radii less than 1 over m, the measure of a ball centered at A of radius r is comparable to r to the s with constants depending on m. So notice that as m increases, the upper L4's regularity constant increases, and the lower L4's regularity constant decreases, and moreover the bound on the radii gets smaller. And so the condition for being inside this set becomes less and less restrictive. And so that means that E will be the union of all these sets A sub m. So if we can show that the tangent measures of almost every point in a fixed one of these sets are always L4's regular, then we'll be done, since the same argument will apply to all the other sets. So we'll just let A be one of these sets A sub m. Recall that by the last theorem in the first video about tangent measures, for almost every point little a in big A, when we blow up the measure mu and mu restricted to A, using the same sequence of radii and constants, the limits will agree with each other, and in particular the set of tangent measures will equal each other. So we're going to fix such a point A. Now, also recall that because the densities of the measure mu exist at almost every point, this means that mu, or since the densities are assumed to be positive and finite at every point in our set, that means that the measure mu is pointwise doubling. So another result that we've seen says that for any tangent measure nu inside our set, we can find a sequence of radii going to 0, so that for some constant c prime bigger than 0, these particular blowups of mu will converge to a constant times nu. And also recall that by our choice of A, so we picked it to be a point where blowups of mu and blowups of mu restricted to A coincide. That will mean that if we look at the same blowups for mu restricted to A using the same radii and the same constants, the limit will give the same measure, C prime nu. Now, since the point A comes from A sub m, the measures of the balls are comparable to r sub I to the power s. So that means that we can pass to a subsequence so that the ratio of the mu measure of this ball divided by ri to the s converges to some constant. So what that means is that we can swap out these constants here with just ri to the s, and these will still converge to some multiple of nu, although perhaps a different multiple than before. Now, by rescaling the measures if necessary, we can assume without loss of generality that this constant is 1. So in the end, what we have is a sequence of radii going to 0 so that these blowups of mu and the same blowups of mu restricted to A converge weakly to the same measure nu. So let's recap what we have. We have a set A so that for small radii and any point little a and big A, the measure of the ball centered at little a is comparable to its radius to the power s. We fixed a point A where the tangent measures of mu and mu restricted to A coincided. Then we fixed an arbitrary tangent measure nu and chose a sequence of radii going to 0 so that the blowups of mu and mu restricted to A inside balls centered at A of these radii both converge to the tangent measure nu with constants both equal to ri to the minus s. Let's call the sequence of blowups of mu sub I. Our goal now is to show that for every x in the support of nu and positive radius r, the nu measure of the ball center at x of radius r is comparable to r to the s. If we can find balls, let's say of the form BAI r over 2 contained in BXR, where the AI are inside the blowup of the set A, then the nu measure of the ball center at x of radius r will be at least the lim supremum of mu I of BXR, because the mu I, recall, converge weakly to nu. And because these balls BAI r over 2 are contained in BXR, this limit supremum will be at least this one. And recall that the mu measure, recall that for small balls centered on big A, the mu measure of small balls on this set A will be comparable to their radii to the power s. So thus, the blown up versions, so mu sub I of balls centered along the blown up version of A will also have a measure comparable to the radius to the power s, but not just for small radii. In fact, any radii will work so long as r sub I is small enough. Okay? So thus, the limit supremums of these balls will be at least a constant times r to the power s. And thus, that will prove the lower regularity of the measure nu for the ball BXR. And a similar argument by approximating by balls centered on the blown up version of A containing BXR will prove the upper L4's regularity bound. But why can we find such balls in BXR centered on the blown up versions of A? Well, below is an illustration that describes the main idea. So imagine a picture on the left. The dots denote the set A, and the shaded ball is a ball centered at little a of radius ri. So this is the ball that we're blowing up with. On the right is what happens when we blow up this ball. So the dots are the image of A under the blow up map TARI. So it's TARI of A. And finally, the shaded ball on the right is the image of the shaded ball on the left. And so now this shaded ball on the right is the unit ball. The blue circle denotes the ball BXR. which is centered on the support of nu. And this is the ball whose nu measure we'd like to estimate. So our goal is to find a red ball centered on one of these dots, so on the blown up version of A, of radius comparable to the radius of this blue ball. But why can we find these dots inside the blue ball anyway? Well, since the blowups of mu restricted to A are also converging weakly to nu, that means that the support of the blowups of mu restricted to A are converging to the support of nu. But the support of the blowups of mu A is just the set A. So that is, these black dots on the right here. So if I is large enough, so that R sub I is small enough, the blowups of A will get closer and closer to the support of nu, and so that means that we can find the black dot that is close to the center of the blue ball. And in fact, by taking I larger and larger so that the ball we're blowing up in is getting smaller and smaller, the blown up versions of A will better approximate the support of nu. And so, in fact, for large enough A, we can find points in the blown up version of A as close to the center of this blue ball as we want, and we can actually approximate the blue ball better by balls whose radii are as close to the radii of the radius of the blue ball as we wish. And those are the main ideas of the proof.